Welcome everyone to this statics lesson. In this lesson, we'll be talking about vectors and just introducing them. So a vector is a value that's characterized by both its magnitude and direction, usually by a set of Cartesian points, but could be otherwise as well. Graphically is defined as an arrow. The arrowhead provides the sense or sort of a direction of the vector. The length is signified by, or the length signifies the magnitude of the vector, and the direction is the line of action, which is the line which passes through the vector. In writing, a vector is noted by an arrow or bar above the vector variable or a bolded vector variable. Some basic mathematical operations on vectors include scalar multiplication, where one would multiply all of the coordinates of the vector by the scalar. Another is vector addition, where we add similar components of the vectors. This is equivalent to adding them tip to tail graphically. What we do is first resolve vectors into their components, x, y, and z, then add the collinear components, and then finally use the components to find the resulting vector. So a unit vector is particularly useful. It's a vector of magnitude 1 that defines a direction. Any vector is a multiple of its unit vector. These don't tell us anything about the magnitude of a particular vector, since they are all rescaled to be a magnitude of 1. These can be found by dividing the vector by the length of the vector, which is the length of the vector is found by squaring the x and adding it to the y squared plus the z squared coordinate and all square rooting. Cartesian vector notation is a useful way of expressing vectors in terms of their x and y and sometimes z components as well. It's written as a sub xi plus a sub yj plus a sub zk, where a sub x is the scalar multiplier or coefficient for the unit vector in the x direction I. A sub z and a sub y are similar. So to convert a rectangular coordinate to Cartesian vector notation, simply replace a sub x with the x coordinate and so on. So for example, the vector 1, negative 2, 3 would be in Cartesian vector notation 1i minus 2j plus 3k. The right-hand rule helps us to find the positive directions. So this will start us with a basis for our vector. So with our right hand configured in the shape below in the image, we can let the positive x-axis be represented by your index finger, positive y-axis be represented by your middle finger pointing towards you, and the positive z-axis being represented by your thumb pointing up. Coordinate direction angles are important. We can form angles between the tail of the vector and the positive axes, alpha between the x-axis and the vector, beta is the angle between the positive y-axis and the vector, and gamma is the angle formed between the positive z-axis and the vector. Direction cosines are important in determining coordinate direction angles. So if we have a vector in Cartesian vector notation, then the cosine of alpha would be a sub x divided by length v, length of the vector, and so on for cosine beta and cosine gamma. We'll do a few examples in this video to do with scalar multiplication, vector addition, unit vectors, and direction cosines. And as well as always, there will be some extra examples linked in the description that deal with scalar multiplication, vector addition, unit vector, and direction cosine as well. So we'll start with these video examples. So first, we'll look at scalar multiplication. So if we want to evaluate 6u, all we have to do is multiply each of the components of the vectors by 6. So u is 3, 7, 4, and 6u would be, so just show that, 6u would be 18, 42, 24. So it's pretty simple. Vector addition is next. So if we want to evaluate u plus v, all we have to do is add the components. And in this case, conveniently, they are already laid out in x and y components, which means we don't need to change them into x and y components. So we're looking at 2, 4, plus 5, 3, and we simply add these. And that would result in vector 7, 7. Graphically, what this would look like is if you have vector u, which is 2, 4, should look something like that. And you have vector v, which is 5, 3, looks something like this. You'd add them tip to tail, so take u, add v, and your resulting vector would be 7, 7. Next is finding a unit vector. So in the problem, we need to find a unit vector for u is 3, 7, 4. So to do that, we need to find length u first. So 3 squared plus 7 squared plus 4 squared, 9 plus 49 plus 16 should equal root 74. And then we'll take vector u, which is 3, 7, 4, and divide it by its length. Okay, and that is the unit vector for u. Finally, we'll look at direction cosine. We want to find alpha of vector u. Note that cosine alpha is simply ax over length of u and u is equal to 3, 7, 4. that AX is equal to 3, and that just comes from here. And we've already found in the previous example, the length of u rather, is 3 squared plus 7 squared plus 4 squared equal to root 74. So then, we manipulate this formula and find that alpha is equal to inverse of cos, or arc cos, a sub x over length of u equal to arc cos, or inverse of cos, of 3 over root 74. And this is all equal to, rounded to the nearest degree, 70 degrees. All right, that is it for today. Thank you for watching. As always, there will be extra examples along with these links posted with an annotation in the link below. Thank you very much for Google Keep and Tulum as well for their